Okay, I want to do a little breakdown of what I got going on here. I had some earlier videos that kind of showed, the bench stuff and some pictures, and so this is with it installed, and it's on the back side of the printer. And then on the other side of this plate, I have the four servo drives, and then this lower plate is my high voltage side, the 220 volts, and then this is all the low voltage side here. I'm using circuit breakers, a line contactors. There's four of them here. I've got an SSR here to turn on and off these contactors. And if you look here, really important on inductive loads, which coils are inductive loads, that you have a diode on the SSR's output. I promise you, if you do not use a flyback diode or a diode on the output, when that contactor shuts off, it's going to induce a nasty spike back to your MCU wherever it's connected, and it will cause it to shut down and reset. Don't ask me how I know. And so, circuit breakers, we got our incoming 220, our circuit breakers, contactor, SSR. We have our four line filters, and then just some terminal blocks to send the wires out. And then up here, I wanted to note that I've made a change here on this guy, and this here is a relay board. There's four relays there. They're SSRs, and I'm using them for my emergency stop or fault handling, basically. So since I have I have two servos for each axis, and if one servo faults, the other one would try to continue to run, and then that would cause the gantry to skew, and I don't want that. That could cause a lot of problems with the carriages, with the balls in the carriage, crashing and so forth. So what I've done is I'm using this for my fault handling, and I've got the drives configured so that fault output is normally closed. So as soon as the drive is energized and there's no fault, each drive will energize one of these relays, and then it in turn sends a signal back to the drive for fault handling of halt, basically. So, and then these particular SSRs have a normally open and a normally closed side. A lot of the ones I see usually only have normally open, and so this one has open and closed, and I'm using each of those contacts for indication. So these four wires that are longer are going back to the breakout board and then to the MCU. That'll tell the status of these when Clipper does finally update the status of those decode buttons. And then directly the wires go back to this board here, and those four are lit right now, meaning that each drive is faulted and they are in emergency stop state right now because those four lights are lit. And these are wired in such a way in series that if any one of these relays is off, none of the drives will run. It'll put all of them into an e-stop condition or halt condition, and you can specify how you want that halt condition to operate in the drive, whether you ramp to stop, coast to stop, dynamic brake to a stop, hold position. There's many options on how you can handle how you want the drive to respond in case one of them faults while you are running. If one of them faults, since Clipper doesn't actively monitor the status of those drives, and especially since it can't in real time, it's just not fast enough to handle any I/O in real time from those drives. So Clipper just does its own thing and says go, 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 and the steppers, they just try to follow it. And then eventually when the G code is updated in Clipper, it'll catch whether or not one of these is actually shut off, and it will cause it to disable the X and Y axes at some point. Now, instantly, whenever this happens, whenever one of these shuts off, it'll kill all four almost instantly. And so that's kind of how I've got that done here. I'm using these are my I/O boards, so I'm sending out 3.3 volts here, and then output is going to 24 volts here back to the drive. So these lights that are on now, I don't remember what they're. This is a fault status, I'm pretty sure, these ones that are lit. And then you have other ones for servo on or enable drive. Also for your position referencing. In one of my other videos I mentioned that I'm going to use the home function of the drive to only move the servo to the Z marker, which happens once a revolution. So it's a lot better that if you home to the end stop and then you use the drive's home to Z marker pulse, and then your home position will be pretty much exactly the same every time. And then what's kind of neat about that is you can offset the Z marker. You can't offset the physical marker position, but you can offset the encoder's position however much you want in order to get your gantry to be square, you know, and not skewed in any way. So you have to put some indicators on there and so forth, and then check it, and then change and finally get the number that's magic, that makes everything square. And so that's how I've got it set up to do on this machine here. And originally I had one of these boards in place of this board up here, and this basically takes 24 in and outputs whatever you want on the other side. This one in particular is for 3.3 volts out, but they will work. I'm sure this will work at 5, but at some point this is not going to work because of the resistors that they have here in front of the optocouplers. So it's going to be limited on a certain range unless you buy a specific model that covers. See, this one is marked on its input and output. But like I said, you can vary from that a little bit based on those resistors. And I just had to put this to the side now in favor of the relay board. So I like this a lot. This works really good. I've did quite a bit of testing with it, with the motors on the bench, and then running max pulse rate tests and causing the drives to fault. Actually, the MCU is the one that faults. It'll fault with a stepper in the past alarm if you generate too many steps. So this is a STM32H723 MCU on a development board, and it's got 60 pins on one side and another 60 on the other. Most of those you can use as GPIO, and that's what I'm doing here for my G-code buttons, you know, for the fault handling, and also for my step and direction signals. And I'm not. You can output directly from the pin of the MCU to the drive for pulse and direction, but it was recommended that you go with a TTL line driver and convert those GPIO signals to a 5-volt differential for noise immunity, galvanic isolation. So I went ahead and did it. It works just fine. These produce a really nice square wave. And right now I'm running 10,000 steps a revolution, and on 4 independent drives I'm limited at 10,000 steps a rev to about 4,500 RPM. I really don't need 10,000 steps a revolution. It's pretty high, but I wanted to see what the maximum was, and I may move it down to probably around 5,000, but really I'm not going to go 4,500 RPM. It's a little high. That 4,500 RPM would probably be around oh Lord, I don't even know what the millimeters per second would be at 4,500. I think 2,000 is 1,500 millimeters a second, something like that. So I'd have to look at my little table. I don't quite remember, but 4,500 is plenty. And that resolution, 10,000 steps a rev is, you know, if you're traveling 40 millimeters in one rotation, 10,000 steps is around 0.004 millimeters of resolution. It's way too high. It doesn't need to be that high. I think 5,000 is plenty. I think most recommend like 4096. Why they choose 4096, I don't know, but you can use 10,000, 5,000, 8,000, whatever, it doesn't matter. And yeah, I've been printing with it a little bit, and I do have some issues with corners, with 90-degree corners. But this is the very initial setup of this machine. I've only printed a few things with it. I printed this vase here. It actually came out pretty decent. This was a flow of around 60. It really came out pretty good. Curves work really well. I don't really see an issue with those. But on 90-degree corners, I'm seeing there's like a delay, or I don't know if it's overshoot. I don't know yet. It more than likely is drive tuning. There is an auto tune function on these drives. It does seem to work. They are pretty stiff, the motors are, but I need to run more tests to see what the overshoot is at what different speeds, and see what the acceptable amount is for a given speed. And currently the motors are inside the chamber, and I need to move those out of the chamber due to basically temperature. Those motors have a rated temperature of around 40 C ambient, and they're derated at 10% for every 10 C, I believe it is, over 40 C. I did run them in the chamber, and they get not a completely closed chamber. I probably was 50 C, and the motors internal were around 60, I think, around 60 C. So I didn't have any problems, but that's just what they recommend, and I would like to have them out of the chamber as well. And when I do put them out of the chamber, I'll more than likely double the motor torque by gear driving at 2 to 1. That way I can get much better mechanical resolution, and that should do better for overshoot by doubling the mechanical resolution. I think that's going to be the way to go. These motors can spin 3,000 RPM at full torque. Full torque is around 0.3 Newton meters on these 100-watt servos, and they have a peak of around 1.2 Newton meters. And when you print, you can hear this chirp noise, and that chirp noise is those drives using above 100% torque in order to do the job. At least that's what I believe it's doing. I'm pretty sure it is, actually. So I'd like to double a 2 to 1, at least 1.5 to 1 reduction, and up to 2 to 1. And so more than likely I'll be moving them externally, but I do want to run more tests to see if I can get at the same quality level for the same speed that I had with steppers. So far, to me, the sound reduction is amazing. You can't even hear the motors run. You can hear the Z, you can hear everything else above the motors run now, and they're just amazingly smooth. I did some tests already. I don't see VFA. I need to run more tests. I'm sure there's going to be some VFA of some sort, but I want to see how it compares. Does it change with speed? Does the frequency of the VFA change like it did with steppers, or am I only going to see a 2mm VFA from the belt? Whereas before, when I VFA tested at different speeds, the speed caused the frequency of the VFA to change. They got wider or narrower based on the speed. So that was leading me to believe that steppers are the cause of the VFAs that I was seeing. So there can be VFAs from other things like the belts and the teeth and so forth. And I'm going to kind of compare some of my previous prints to this new setup and kind of see where it's gone from here. I will say that this is really a big messy project. I mean, you can see the whole back side of my printer is covered in electronics. Okay, I will make covers for these. This is a temporary thing. There's a 2020 extrusion here, and this is just bolted to the back side here. If I need to, I can just pull this stuff off and I can use these same plates, or I can keep everything wired like that and mount them to another plate, or if you wanted to, you could take these and put them in an external enclosure and you could put them next to the printer, and you can go about it that way as well. That actually is probably a good idea, a separate panel. But I can see where a solution like a ClearPath, having an all-in-one motor solution, is a lot cleaner, and that everything is inside that motor. Now, I don't know the performance difference between a ClearPath and an AC servo. I don't know that. I'm sure it's pretty good. But I don't really know. I don't know. I don't know how they compare in that respect. Servo's supposed to be more accurate, but like I said, I really don't know. There's differing examples everywhere. So anyway, so this is what I got for now. Enjoy.